Hello, everyone. Uh, Thank you for joining me today. I will be giving a presentation on memory safety without runtime checks or garbage collection. Um, what is an embedded application? An embedded application is a software application that permanently resides in an industrial or consumer device. And current embedded applications require a lot of flexibility as well as speed. Um, Current system approaches for ensuring memory safety require significant overhead in terms of runtime checks and garbage collection. And this overhead slows down such applications up to 20%, which is not ideal. What is the solution to this problem? The solution can be to develop an algorithm that does not rely on neither runtime checks or garbage collection. One of the main problems with ensuring memory safety uh, without relying on runtime checks or garbage collection is the safety of dynamic memory allocations and allocations. Uh, One proposed solution to this problem is an algorithm called region-based memory management algorithm. It guarantees the safety of point-based memory accesses. However, it does require significant manual effort. This allows explicit delocation of individual objects, requiring data structure that shrink and grow frequently have to use a separate garbage collected heap to avoid unnecessary memory usage. So this brings up the question of whether there is a better algorithm that can have all these features but minimize the overhead, um, minimize the overhead that the current algorithm is um, using. Okay, so four researchers from the University of Illinois came up with this algorithm called automatic pull allocation. And this algorithm puts minimum syntax restriction on a given embedded code. It is only tested in C codes. So automatic pull allocation algorithm. So what is it? It is an algorithm that automatically retains explicit delocation of individual objects within regions or pools. Each pool holds object of a single size, thus eliminating fragmentation within pools and enabling very fast allocation and delocation. By the way, fragmentation is an unwanted problem where the memory blocks cannot be allocated to processes due to their small size and blocks remain unused. Uh, okay. Back to the slides. It does not ensure memory safety due to possible usage of dangling pointers. And dangling pointer is a pointer that points to invalid data or data which is not valid anymore. The objective of the author's research is to ensure memory safety without requiring runtime checks while retaining the performance and memory benefits of the automatic pull allocation algorithm. How? You might be asking how. Well, the author's current work did not eliminate the usage of dangling pointers, but ensured type safety for such operations. In procedural flow analysis of the compiler-generated pull operations. Assumptions. So the authors assumed that certain runtime errors were safe, as the runtime system can recover from such errors by killing the process. The programs had a reserved address range, and any access to these addresses caused a safe runtime error. Certain libraries functions were trusted and can be invoked by untrusted code. Source codes were available to the compiler, and the programs had to be single-threaded. So let's start off talking about the safety of pointer references. Three ways for a pointer to result in unsafe memory behavior. It can be through initialized pointer variables that can access the invalid memory addresses, a pointer into a static frame of a function that can be used after it returns to an access of object of some kind. A dangling can be used to access an object of different types allocated later. So the authors enforce some rules to ensure the safety of a pointer. These include every local pointer variable must be initialized before referenced. Any individual data type not included in an array should be no larger than the size of the reserved address range. Lastly, the address of a stack location cannot be stored in a heap allocated object or a global variable and cannot be returned from a function. Stack safety. The authors the author's work ensured stack safety by not permitting to place the address of a stack location in any heap allocated object, global variable, or returning it directly from the heap to avoid the potential problem of the address of a local variable being accessed after the function returns. They also enforced this rule requires a complicated compiler technology. In other words, to enforce this rule, the compiler had to work with complex systems and complex algorithms. However, the technology used for enforcing heap safety using automatic pool allocation algorithm was enough to achieve the described goal above. So they didn't need a compiler that could work with sophisticated technology. They also use data structure analysis and intraprocedural analysis where they compute a data structure graph for each procedure. But now you might be asking, why is it useful? Well, it is a simple. What is it and why is it useful, right? Well, it is a simple graph of all the memory objects accessible within a procedure, along with their types, their storage class, and links between them. So the author's goal was to create this data structure graph and simply traverse it for each function to ensure the safety of dangling pointers, so that no dangling pointers points to current stack frame. Heap safety. So heap safety is a big challenge for not restricting dynamic object allocation and allocation while also not using runtime checks or garbage collection. So detecting unsafe accesses to free memory is a particularly challenging problem for a language with explicit memory allocation. It is because compilers statically cannot identify which references are safe and which references are not in case of dangling pointers. As you can see the code on the slide, we can see that we create a linked list and then we remove every node in that linked list except the head, and then we try to use that head to reference the next node. But how can we fix this? The authors used the approach that if a freed memory block holding a single object were to be relocated to another object of the same type and alignment, then the referencing dangling pointers to the previous freed object cannot cause a type violation. The authors could separate, following the logic above, the heap into disjoint pools for distinct data types and not allowing memory use for one pool to be reused later for a different pool. It is not efficient due to possible increase in memory consumption. So this again brought up another question that what if there's a better solution? Well, you guessed it right. There's a better solution, and it is called the automatic pool allocation transformation algorithm. It is a more sophisticated way of using the approach described in the previous slide to avoid memory increase as much as possible. How? It uses type homogeneous pools with much shorter lifetimes. Some background information about the alg transformation is a pool is created before the first allocation for its data structure instance and destroyed at the point where there is no accessible reference to data in the pool. Authors use a pool allocation library with 5 simple operations. These operations are pull init, which initializes a new pool, pull destroy, which destroys a pool from the memory, pull allocate array, and pull free. The transformation uses malloc and C's malloc and free methods for updating and or returning memory from the heap as necessary. Heap safety continued. The pool transformation operations as follows. First, the transformation identifies the data structure instances, meaning identifying maximum connected subgraphs containing only heap nodes. Each subgraph represents a distinct heap allocated pool. Second, identify when to create and delete pools. And third, transform delocation operations of functions interfaces, meaning transform all malloc and free calls into original program to use the pool allocation versions. Results. This approach is that this approach, all heap allocated objects are assigned to a type homogeneous pools and individual items are allocated and freed from the same points that they were before. A pool is destroyed before the heap whenever there are no more references to the data in the pool. I included an example on this slide to show you what a good example of pool allocation transformation. Okay. Exploiting pool allocation for heap safety. The homogeneity method earlier can be used to enforce memory safety after pool allocation transformation. Since the pools are type homogeneous already, it should be ensured that methods within some pool P1 is not used for any other dynamically allocated data until it is destroyed. Possible cases include no use. This is between any pool free pool P and the pool destroy for P. There are no calls to PLEC from any pool, including P itself. Second case, self-reuse. Between any pool free operations on pool P and the call to pool destroy for P, the only pool alloc operation are the same pool P. Third case, cross use. Between the first pool free operations on P and the pool destroy for pool P, there are no pool alloc operations for the pools. There's an example below that gives some sort of insight of how each case is used. Array safety. Authors put a certain number of semantic restrictions on array usage. Trusted libraries. They allow trusted libraries routines. However, those routines had to satisfy some safety conditions to prevent buffer overruns within the library routines. Also, to ensure the safety of string routines, the authors added a rule to the last element of an array always must be initialized to null to avoid it from reading beyond the size of an array. The benefits of using library routine is that it allows body of library routine to use a non-FAN array accesses or non-type safe code. Summary. How did the new work differ than previous work? So, with the current work, authors could actually they got closer to finding a solution to dynamic memory allocation problem. However, array-based accesses remained as an obstacle as before. The safety of stack, heap, and pointers has been achieved. They used 17 diverse benchmarks to test their algorithm. New rules were added to allow the usage of certain trusted strings and I/O library routines, which are widely used in embedded codes. For test results, um, the algorithm performed a good job on ensuring heap pointer safety. All the cases were passed. For stack safety, 16 out of 17 cases passed, which indicates that the current algorithm can ensure stack safety as well. However, for array bound checking, only 9 out of 17 test cases passed. So this is an indication that future works can be more focused on array bound checking and ensuring that array-based accesses is also ensured and no memory leak or memory safety is obtained. Critique weaknesses. One problem with the current work was that there was not enough background information on the controller programs, which the authors use in their previous work versus other embedded applications with complex memory management. There wasn't enough work, there wasn't enough information about comparison of the algorithms to existing technologies. There could be better explanation of why existing technologies are used and how they really differ from the author's algorithm. There could be a bigger and more diverse data set. Instead of just 17 benchmarks, they could come up with more than 17 to really show that their algorithm works. Also, compilers are a big part of this workflow. However, there was a lack of details on the work of the compiler through the execution of the programs. And the authors didn't talk about future and current compiler techniques, which I thought was important to grasp the information they were providing. However, on the good note, the solutions to heap safety and other methods were very well explained, and they included visuals to enforce our understanding. And they also provided step-by-step instructions on how the automatic pool allocation to transform the program into the desired state, which I found interesting. Conclusion. The authors mainly focus on dynamic memory allocation delocation using the automatic pool allocation algorithm. The results indicated that they have achieved their goal for ensuring memory safety for heap, pointer, and stack without relying on runtime checks or garbage collection. The algorithm used in the research has failed to ensure memory safety for complex array references in memory. This is a great research topic as it can certainly help the current and future embedded applications in terms of performance and flexibility if the safety of an array references can be guaranteed in the future work. Here's the references. Here's my contact information. If you'd like to learn more about this research or ask me questions, please feel free to contact me at amb190-003 at utdallas.edu. Thank you so much.